Morning, everyone. We are recording now, and let's see. Okay. So today, I just want to quickly mention a point I forgot to mention in the last lecture. So towards the end, we proved that. Right. So we proved that you can look at orthogonality of the cycle space and the bond space via the lens of duality. So in the case of a plane graph, if you have a connected plane graph G and you have the dual G star, the plane dual, then whenever you look at a cycle in the graph G, the corresponding edges, they form a bond in the graph G star. And likewise, every bond translates into a cycle in the dual, right? And we proved one part of it. The other part is an exercise, might be on your assignment, I'm not sure. And I forgot to mention the corollary. Because the cycles translate into bonds and vice versa, one corollary is that the cycle space of the graph G is isomorphic to the bond space of the dual G star, right? So here we are talking about two vector spaces being isomorphic. Okay. Good. So that's all I want to tell you about the about planar duality for now. Let's move on to a topic that most of you have seen in your previous courses, perhaps all of you. And so I'm going to keep this one a bit fast, and I won't go into too many details. Just want to remind you of all the important things and then move on to the next topic in this module. Okay, so let's discuss Euler's formula. So, well, I'll just write it down straight away since you've probably seen it anyways. For a connected plane graph, so typically it's written as the number of vertices of the graph minus the number of edges of the graph plus the number of faces of the graph is 2. From the point of view of proving it, I prefer to get rid of the minus signs because I think it just makes it easier to see the proof. So the number of vertices plus the number of faces is equal to the number of edges plus 2. Right? And let's just do a quick proof sketch of this. So this must be from 1700s since it was proved by Euler. So there is a class of graphs for which this is very easy, given that we have already assumed the following fact. In any tree, there is exactly one face. Any plane tree has precisely one face. Okay, so supposing you have a tree, so the proof is by induction on the number of edges of the graph. Supposing you've got a tree, okay, then let's see what this is saying. We are trying to prove that let's call it T because T is a tree generally. So we are saying that the number of vertices of the tree plus the number of faces of the tree is equal to the number of edges of the tree plus 2. Right? We want to verify this. Well, you know that the number of edges of the tree is the number of vertices of the tree minus 1. Right? We have got the number of faces of the tree to be equal to 1. And now you can see why this is true. Right? Both sides are equal to number of vertices of the tree plus 1. Right? So that's done for trees. And now the next case is when your graph is not a tree. That is the same as saying that there is an edge that is not a cut edge, because trees are the only graphs in which every edge is a cut edge. So there exists an edge E such that E is not a cut edge. Okay, so we're going to look at the graph G minus E, and we know the statement is true for that graph by induction. And now what happens in the graph G when you add the edge E back into the picture? So by induction hypothesis, we know that the number of vertices of G minus E plus the number of faces of G minus E is equal to the number of edges of G minus E plus 2. Right? This is true. So now let's think about what is going on when we add an edge to the graph, which is not a cut edge. Well, every edge that is not a cut edge is incident with two faces. In particular, what's happening is that you have some face and you are adding an edge that is not a cut edge, and therefore you create one more face. Your original face splits into two faces. So the number of faces goes up by one. The number of edges goes up by one, well, because you added an edge, and everything else remains the same. So in other words, you're adding one here and you're adding one here when you go from G minus E to G. So clearly, the equation holds. Okay, so that is a proof. Okay, so we are done. The number of vertices of G plus the number of faces of G is equal to the number of edges of G plus 2. Okay, good. So that's a proof of Euler's formula. Any questions or concerns? Okay, so if not, let's discuss some consequences of Euler's formula. Well, the first consequence is that it tells you that the number of faces of a plane graph or of a planar graph is actually invariant, because the number of faces can be written as the number of edges minus the number of vertices of the graph plus 2. And all of these quantities, they do not depend on an embedding. Well, the left side depends on the embedding. So that means that for any two different embeddings, you will have the same number of faces. They may not be the same faces
Sir, we couldn't hear you for some
Okay.
time.
Yes. Sorry. I got disconnected, but now I'm back. So, what was the last thing you heard me saying?
I heard you say that the right side is invariant of
Right.
embedding and
Exactly.
the left side is. Yeah.
Right. So, exactly. So, the number of faces, um, while it depends on embedding, the right side does not. And so, one consequence is that any two planar embeddings of a planar graph will have the same number of faces. Right. So, that's a corollary 10.20. All planar embeddings of a planar graph have the same number of faces. Okay, good. So that's one consequence. There are some other consequences of Euler's formula that I want to mention. Um, well, basically, there's one more point I want to mention. So intuitively, you would think that a planar graph cannot have too many edges, right? You would think that if you have too many edges with respect to the number of vertices, then your graph would be non-planar, right? And that intuitive thought is actually true. Of course, you have to be careful. You have to consider simple graphs, because if any graph is planar, you can add as many multiple edges and loops, and the resulting graph will still be planar, right? So we need to be careful. We need to talk about simple planar graphs. And then the intuition that there can't be too many edges is actually true. And one can prove that easily using Euler's formula. So what we will prove is that the number of edges is actually linearly bounded by the number of vertices. In fact, we have a precise formula which is best possible. Okay. Okay, so let's, before we write down the statement, let's try to see what is the bound we can get. Okay, so we are going to use the following. Let's say we have a planar graph, simple planar graph. We want to prove that the number of edges of the graph is bounded by the number of vertices, some linear formula. Right, so linear in the number of vertices. Okay, so well, what are the tools we have? I'll take a planar embedding of the graph. And let's see, supposing I sum up the lengths of the faces or the degrees of the faces, I would get 2 times the number of edges, right? So if I take all the faces of the graph, what I would get is 2 times the number of edges of the graph, right? But the length of any face in a simple plane graph should be, it can't be really 1 or 2 unless your graph is really, really small. Now in this case, the length would be 2, right? But in general, you would imagine that if you think of all faces being bounded by a cycle, but it's true even otherwise, then every face will be bounded by a cycle of length at least 3, right? But they may not be bounded by cycles, but you can still prove that the boundary of any face will have length at least 3, so long as your graph has at least 3 vertices, right? So this means that on this side I can write 3 times the number of faces of the graph, right? This will be a lower bound on the sum of the degrees of the faces, right? And this quantity, using Euler's formula, we can write in terms of the number of edges and vertices, right? So it's the number of edges of the graph minus the number of vertices of the graph plus 2. Okay, and what does this give us? 3 times the number of edges minus 3 times the number of vertices plus 6 is less than equal to 2 times the number of edges, right? And this gives you that the number of edges of the graph is less than equal to 3 times the number of vertices of the graph minus 6. In other words, m is less than equal to 3n minus 6. Okay, and that is exactly the formula we have. So long as your graph has at least 3 vertices. This you need in order to establish this inequality. Okay, good. So here we are just using Euler's formula, and here we are using the dual handshake lemma, right? Also, I didn't mention, but you already probably see it. The reason this is called the dual handshake lemma is because in the dual graph, this will exactly be the handshake lemma, because the degrees of the faces become degrees of vertices, and we know that the sum of the degrees of vertices is 2 times the number of edges, right? So what we have here is a linear upper bound on the number of edges in a planar graph, in a simple planar graph, in terms of the number of vertices, right? And this gives you a proof of why K5 is non-planar. So if you don't want to go through Jordan curve theorem, although in reality everything really depends on Jordan curve theorem, um, somewhere or the other it is being used. This gives you another way to prove that K5 is non-planar, because 3n minus 6 in the case of K5 would be 15 minus 6, 9, and K5 has 10 edges, right? So, okay. How would you prove that K33 is non-planar using a similar argument? Anyone? Does this corollary prove that K33 is non-planar? Does this imply that K33 is non-planar? The bound that we found. No, right? You can do the math, the arithmetic, and you will see that it does not imply that K33 is non-planar. However, K33 has another property that we can use. Anyone? What is the property of K33 that we could use to get a better bound on the number of edges? Exactly. K33 is bipartite. So the length of a face would not really be 3. It would be at least 4. So I think you need the number of vertices to be at least 4 or something. Doesn't matter. And what you can prove is that in the case of bipartite graphs, you have a stronger upper bound. So I'll leave this as an exercise. Do it yourself. Prove a stronger upper bound for bipartite planar simple graphs, and using this strong upper bound, deduce that K33 is non-planar. This might have already been an exercise on your previous course. It's a very standard exercise. Okay, so it's very similar to what we just did, so I won't do it here. Okay, good. And another do-it-yourself, which will be useful to us later. This is a corollary 10.22 in the text. Every simple planar graph has a vertex of degree at most 5. This will be useful to us when we go to coloring graphs, which is the next module after planarity. Right? Intuitively, this seems true. You can't have all vertices have high degree because you have a linear upper bound on the number of edges. And in fact, what you can prove precisely is that there is always a vertex of degree at most 5. And using this, we will be able to prove that you can color every planar graph with 6 colors, whatever coloring means. We will define that in the next module. But if you already have seen colorings, then this corollary immediately implies what is called the 6-color theorem or the 6-color proposition. Okay, good. So that is all I want to tell you about Euler's formula and its implications. Are there any questions at this point? All right. If not, then let's move on to the next topic in this module, which is basically starting our journey towards proving Kuratowski's theorem. Okay. So those of you who took my previous course, you've already seen this topic as well, bridges of cycles. But you didn't see a proof of Kuratowski's theorem, so we will be doing that in the next 1 or 2 lectures. Okay. So let me start with an example. Okay. And while I draw this example, I want you to remember the definition of a separating vertex, not the formal definition. I want you to try to remember the intuitive definition that we discussed in the lectures using a 3D model of your graph and a scissors. Okay. So that turns out to be a good way to think about this next topic as well. Okay, so I'm going to draw this example straight from Bondi Murthy. Okay. All right. Good. So this is a planar drawing. Do I want it to be planar? Let me make a crossing because I don't care for it to be planar. Okay, good. Just to make it a bit. Um, all right, this is good enough. So I want you to look at this graph here. It's not a planar embedding or anything. You see there is a crossing. So what we are going to define is something abstract, does not rely on the embedding of the graph. Okay. What you have is a graph, and you have this cycle. Um, let me make this cycle. Okay, I'll just color the vertices of the cycle so that you can see the cycle. Right, it's the first cycle I drew. Okay, so you have a graph G, and you have C is your cycle with these solid vertices and the edges joining them. Okay, good. So I want to define what are called bridges of a cycle. Okay. And first I will give you an intuitive definition, right? Without going through the formal rigorous definition. Here is the idea. Imagine a 3D model of your graph, right? Like we did before when we were defining separating vertices, where all the vertices are represented by beads and all the edges are strings joining those beads. Okay. And So you have this 3D model made of beads and strings. And I give you a scissor and I'm asking you to cut out the given cycles. I'm giving you a cycle, which is simply a string, I mean, a sequence of strings and beads, right? And I'm asking you to cut out this cycle from the rest of the graph using scissors, right? So you can use the scissors and cut the strings. So what you would do is you would cut the cycle out as follows. Let me use black, or maybe I'll use red. Okay. So what you would do is you would put a scissor cut here. You would put a scissor cut here, a scissor cut here. Likewise, you would have to put the scissor cut here, but to cut out this loop, you will have to put it twice. Okay. And likewise, you would keep cutting with scissors in all these places. Okay. Am I missing anything? If you put scissor cuts in all these red places that I have marked, then you would be able to cut out the cycle from the rest of the graph. You agree? And now you have the cycle and you have other pieces of the graph. These pieces are called bridges of the cycle. Okay. There is one problem. You have pieces that don't have the end vertices. For example, this loop would become a piece like this, right? Similarly, this guy here would look like this, right? So these are not really graphs, right? We would like to have graphs. So we are also going to include the vertices where they join the cycle. Okay, we are going to include those vertices so that we can define things rigorously without introducing objects that are not graphs, right? Is it clear what the definition is? Is it clear what a bridge is? So let's draw all the bridges of this graph using different colors so that it's even clearer. So one possible bridge is this blue colored subgraph along with the three vertices that are here, right? But for the sake of convenience and to not make things very confusing, let me not mark the vertices, okay? Just assume that the vertices have to be taken whenever the edges incident to that vertex are taken. Okay, so this is one blue colored bridge. Then you have a bridge here, which is a green colored bridge. Okay, I'm using colors just to illustrate what the bridges are. This here is a red colored bridge. Okay, and so on and so forth. How many bridges do we have in total? Can anybody tell me how many bridges are there? I've already marked 3 of them. How many more bridges do we have? 6. Exactly. So all of the bridges have some vertices which are not in the cycle, except for 2 bridges. One is the loop, and there is one more bridge which doesn't have any vertices that are not on the cycle. This guy, this is a chord of the cycle, right? The loop can also be considered as a chord of the cycle. So this is a bridge. This is called a trivial bridge. And this one is also called a trivial bridge. All the others are non-trivial bridges. Okay, so hopefully the intuition is clear. And now let me put down the formal definition. Before I put down the formal definition, let me point out the motivation for this definition. We are discussing planarity. So whenever you have a cycle, you're going to embed it. You're trying to get a planar embedding of the graph if the graph is planar. Okay, so whenever you have a cycle, you will embed it in the plane and it will look like a closed curve. And what I want you to observe is that every bridge of this cycle will either have to go in the interior of the curve or in the exterior of the curve. And that is the motivation for this very technical definition that we're going to write down, right? All right, so let's put down the definition. So G is your graph, C is your cycle. What we are going to do is we are going to partition the edge set of the graph, those edges that are not on the cycle, as follows. Right, so these partitions are basically the colors I was using. So there are non-trivial parts, or yeah, non-trivial parts, or we will call them non-trivial bridges. So what you do is you delete the vertices of the graph and look at any component. Supposing let J be a component of the graph minus the vertices of the cycle. So if J is a component, then consider the set of edges of the graph J, of the component J, along with all the edges that join J to the cycle. This is the same as partial of the vertex set of J, because all the edges that are leaving J, they will have to land on the cycle. Right? So to give you an example, if when you delete the vertices, you get this component J, which is this cycle, 4 cycle. You will take all the edges of this subgraph J along with all the edges that join J to the cycle C. And that is one bridge of your graph. Right? So these are the non-trivial bridges. And then you have the trivial bridges. So this will be your non-trivial bridge. Now, supposing E is any edge, which could be a loop, that has both ends in the vertex set of the cycle C. Then you will have a bridge with just that edge. Or if you want to view it as a subgraph, it will be the edge and the ends of that edge. Right? So examples of trivial bridges, as we noted earlier, are E1 and this chord of the cycle E2. You may also want to think of these as chords of the cycle C. Right? It's a term that many of you used on your assignment on induced cycles. Right? So good. And observe that this rigorous definition is exactly the same as the intuitive definition that I gave you using scissors and the strings and beads model. Okay? All right. So bridges may be viewed as subgraphs induced by these edge sets. So what is a subgraph induced by an edge set? We have seen subgraphs induced by vertex sets, but subgraphs induced by edge sets means you just take the edges and you take all the vertices that are incident with any of the edges in your set. Okay? So they are either the subgraphs induced by the edge sets, or you can just view them as the edge sets, and both viewpoints are useful. Or simply as edge sets. Okay? And just to make it clear, what is the relevance of bridges? In any planar embedding of G if G is planar. Of course, we did not use that in the definition. We did not require that for the definition. In any planar embedding of the graph, um, a bridge of a cycle C lies entirely in the interior of the cycle, or otherwise entirely, apparently I can't spell, otherwise entirely in the exterior of the cycle. Okay, good. Maybe I should put capital I and capital E, because you also need to put the vertices of the bridges, which are actually on the boundary of the cycle. Right? Okay. Good. Any questions or concerns at this point? Anything that's not clear? Okay. So, if all of this is crystal clear, then let's put down some more definitions. Okay, let me put down a question before we go into all these further definitions. So, there are two things we want to prove in the rest of this module. One, we want to prove that in a three-connected simple planar graph, all embeddings are equivalent. What I mean is that in any planar embedding of the graph, you will have the same facial cycles. If you look at the boundaries of the faces in any two different embeddings, you will have the exact same boundaries in these two sets. That's one thing we want to prove. Another thing we want to prove is Kuratowski's theorem. Okay. And for both of these, we will find the concept of bridges very useful. Okay. In particular, let's ask the following question. So if you have a cycle C in a graph, and you're trying to get a planar embedding of this cycle, of this graph. So you will put the cycle, which will be a closed curve. And now for every bridge, you will have to make a decision. Does this bridge go in the interior of the cycle, or does it go in the exterior of the cycle? Okay. In particular, when can two bridges both be drawn inside the cycle? And when is it necessary that if you put one in the inside, then you have to put the other in the outside? This should also remind you of the discussion we had when we were proving that K5 is non-planar. We took a three cycle, then we argued that one vertex must go inside and the other goes outside. But then, of course, because the two are joined, we were forced to get a non-planar drawing, right? So the question we are asking is, when can two distinct bridges, B1 and B2, both be drawn or embedded in the interior of the cycle C, where these bridges are bridges of the cycle C, right? So bridges of the cycle C. Okay. So in order to answer this question, we are going to find some more terminology very useful. Okay. So notice that for any bridge, you have these vertices of the bridge that are on the cycle, or vertices where the bridge attaches to the cycle. These vertices will be called the vertices of attachment of that bridge. So notice that in this drawing here, the blue bridge, which corresponds to the subgraph J, has 3 vertices of attachment. And these 3 are also vertices of attachment for the green colored bridge. Okay, so these are the vertices of attachment, and the other vertices of the bridge will be called internal vertices of the bridge. Okay, so let's just put down some definitions. So if C is your cycle and B is your bridge, then the vertices of attachment of the bridge B are basically the members of the bridge's vertex set intersect the cycle's vertex set. Okay, and the internal vertices of the bridge B are basically those vertices that are in the bridge but not in the cycle, right? So which means that if you have a trivial bridge, which is a chord of the cycle, then it will have no internal vertices, and it will have 1 or 2 vertices of attachment depending on whether it is a loop or a link. Okay, good. Also, another term that we will find useful is a K bridge, which means a bridge which has K vertices of attachment. Right? So a chord is either a 1 bridge or a 2 bridge. But if you have a non-trivial bridge, it could have any number of vertices of attachment. If there will be at least 1 vertex of attachment for every bridge. Otherwise, the graph will be disconnected. Right? So in our drawing here, the blue and the green bridges both have 3 vertices of attachment. And these 3 are actually the same set of vertices. Okay, and we have a bridge here corresponding to this vertex and the edges leaving that vertex that has 4 vertices of attachment, right? 1, 2, 3, and 4. Okay, so let's make some observations. If G is connected, each bridge has at least 1 vertex of attachment, and also if G is non-separable, then each bridge has at least 2 vertices of attachment. Okay, and if 2 bridges have the same set of vertices of attachment, we will call them equivalent bridges. So in our example, if we call the blue bridge B1 and we call the green bridge B2, then these 2 are equivalent because they have the same set of vertices of attachment, the same 3 vertices in this case. So 2 bridges are equivalent if they have the same set of vertices of attachment. Okay, good. Any questions or concerns at this point? So we're going to find all of this terminology useful. Don't worry about that. I'm not giving you definitions just for the sake of it. All right. Okay, so let's go back to our argument for why is K5 non-planar. Or let me, for a change, do K33. So let's look at K33 minus one edge. Okay. So notice that you can put this as a cycle: A1, B1, A2, B2, B2, and you have two more vertices, A3, A3 should be right, A3 that joins to B1 and B2, and now you have B3 that joins to A1 and A2. So the edge I have removed is A3, B3. Okay. So if I'm trying to get a planar embedding of K33 minus one edge, well, I will succeed. The problem or the constraint that is imposed is that we have to now put the vertex B3 outside because it needs to connect to A1 and A2. If I were to place B3 here, for example, I would be able to join it to A2 but not to A1. And a similar problem happens when I go here. I will be able to join to A1 but not to A2. So these are two bridges of the cycle, where cycle is four cycle A1, B1, A2, B2. I've got two bridges. If I put one inside the cycle, then I am forced to put the other one outside the cycle. Right? Okay. Why is this happening? This is happening because I have two vertices of attachment of this bridge. Let's call this A3 bridge. So there are two bridges. One is the A3 bridge. So A3 and the two edges incident with A3. And then I have the B3 bridge. And they have vertices of attachment that are alternating on the cycle. Whenever this happens, I will not be able to put both the bridges inside the cycle, or I will not be able to put both of them outside the cycle. Right? So that brings us to one more definition. Okay. So two bridges, B1 and B2, are skew if there exists four distinct vertices of attachment U1, V1. These are vertices of attachment of B1, and U2, V2. These are vertices of attachment of B2. Okay, these are of B1, and these are vertices of attachment of B2. Such that on the cycle, you will first see U1 followed by U2, followed by V1, followed by V2 in that cyclic order, depending on how you traverse the cycle. Such that U1, V1, U2, V2 appear in that cyclic order on the cycle C. Okay, in other words, diagrammatically, what is happening is you've got a cycle and you've got a bridge B1 and you've got another bridge B2, and B1 has two vertices of attachment, U1 and V1, and B2 has two vertices of attachment, one of which is here and another which is here. And now when you traverse the cycle, maybe I made a mistake. Yes, I made a mistake here. I'm sorry. I meant to write U1 followed by U2 followed by V1 followed by V2. So if you go in this way, you will see U1 followed by U2 followed by V1 followed by V2. Okay, so you will first see an attachment vertex of B1, then you will see an attachment vertex of B2, then again B1, and again B2, right? So they are interlaced in this fashion. And in this case, we will call them skew. Okay? And it turns out that the answer to this question that we asked is that whenever they cannot be drawn, it's because either the two bridges are skew or they are equivalent three bridges. And I'll let you think about this and we'll prove it tomorrow. So, turns out that the answer um, B1 and B2 cannot both be drawn in the interior of the cycle if either B1 and B2 are skew, as we just discussed, or they are equivalent three bridges, which means they have the same set of vertices of attachment, and this set has size 3. Okay, and to see this for skew bridges, K33 minus 1 edge is a good example by taking a 4 cycle. For equivalent 3 bridges, I suggest that you go to K5 minus 1 edge and take your cycle as a 3 cycle. Just to visualize what's going on. Okay, and we will be proving this fact written here tomorrow, that these are the only cases when you cannot draw the two bridges in the same side of the cycle, interior or exterior, right? Good. And this fact will be useful to us uh, when we go to the proof of Kuratowski's theorem. Okay, it will help us in finding the K5 or in finding the K33. All right, good. Any questions or concerns? Sorry, there is a lot of terminology, but hopefully I gave you sufficient number of examples, and hopefully the main definition, bridges of a cycle, and its properties like the vertices of attachment. Hopefully these things are clear, and you sort of see the intuition as to why we are defining all these things.
So this will still be true if it's a four bridge or more, right?
Yeah, can you repeat the question?
So like B1 and B2 would still be like still can't be drawn in interior of C if if it has more than four bridges. Like
You
instead
mean
of
they are equivalent four bridges?
yeah.
Yeah, yeah. So the same is true for equivalent four bridges. The point is that equivalent four bridges are also skew bridges. So the skewness takes care of that. Okay. In fact, I would go to the extent of saying that skewness, in some sense, to me, seems like the more plausible condition. The only case where the two bridges are not skew is because they both have exactly three vertices of attachment, and they are the same set. And then they are not going to be skew, and that is why we need equivalent three bridges. But in some sense, skew bridges are the more prevalent ones, although that's not a precise statement. So just stating it as an intuition. Any other questions or concerns? Any definitions or concepts that were not clear, that were a bit rushed? We can go through them again. We can clarify the definitions. So this theory of bridges of cycles seems to have been introduced by multiple people. Using this theory, you can also get an algorithm that I covered in my previous course offering last semester. So for those of you who are algorithmically motivated or inclined, you might want to check out that, how you can get a polynomial time algorithm for planarity. I think it's something like lecture number 15 or something. But in this course, we will not be going through the algorithms and stuff. That is not the point of this course. The person who seems to have done the most extensive research and study on bridges of cycles is Bill Tutt. And not only did he introduce them in the context of graphs, but he also introduced them in the context of matroids, which can be viewed as a generalization of graphs and linear independence in algebra. In fact, there are quite a few topics that we are covering in this course that have extensions and connections with matroid theory. I might mention them again in another lecture, but we will not be doing matroid theory in this course. Right? So if you are curious, you can go check it out. All right. So if there are no other questions or concerns, please feel free to leave the meeting. I'll be here for another few minutes.